Moment.
You are on.
Okay, welcome all at the weekly TCS seminar at Jagiellonian. Today, our guest and our speaker is Sasha Wolff from University of Würzburg. Sasha is the chair of the Computer Science 1 in Würzburg, which includes algorithm and complexity. Well, Sasha did his PhD in 90s. Is it safe to say? Or
Yeah.
And I know that he prepared some slides to show his traveling route within Germany and not only. We're very happy that you're here. Sasha is actually here for more than this talk. You are here for a couple of months, 5 months, 4 months. On invitation of Grzesiek Gutowski. Great to have you here. The floor is yours.
Thanks a lot, Friedrich. It's my pleasure to talk to you, and it's my pleasure to be here in Krakow. It has been a fantastic time, and I especially want to thank Grzegorz for inviting me and for helping me a lot to get settled here. Okay, today I would like to talk about a topic that has come out of a Dagstuhl seminar, where I was in a group with these nice people over here, and it's about a mixture of graph drawing, which is my background, and parameterized complexity exact algorithms, which is the background of some of these people on the list. But first of all, as Piotrek already said, I will say a few words about my background. What could this be? Some random points in the plane? No, not completely. My first actually academic task was to label maps. And so here's a map, obviously, and now you have a rough idea what these points could be. And if I give you the labels, you are all set. So what do these places have to do with me? I was born in Stuttgart, in the southwest of Germany. So because of that, I call myself Schwab, which is not doesn't sound very good in Polish, but the people around Stuttgart are called this way. Okay, then I moved a not so far distance to Freiburg to start university. In Freiburg, I just spent 2 years, from 89 to 91, and then I did a big jump to Berlin. To the Free University of Berlin, and there I finished my studies. I wrote my diploma thesis back then. This was before the bachelor-master system was introduced. And then I also did my PhD at FU Berlin. Before finally going for a postdoc stay to the very northeast of Germany, which was quite an experience in many ways. But then I again crossed the country and went just for a one-term replacement professorship for somebody else to Konstanz in the southwest. And from there, then for a couple of years to Karlsruhe. Back then, it actually was not called KIT yet, but later it turned into that. So the University of Karlsruhe, and there we got our first child, my wife and I, and then just before the second child was about to show up, we moved again to Eindhoven and enjoyed 3 years in the Netherlands. But from there, I still applied to professorships in Germany, and finally I ended up in Würzburg, where I'm up to nowadays. So to add a little bit to this rather German itinerary, let me mention a trip that I did in 1990 already. That was the new year when they abolished the visa duty in to go to Poland. So I still needed one because we arrived before New Year and left afterwards. So I first went to Warsaw to visit a friend whom I had met in Japan sometime before, and then I went for a New Year's celebration, not in Krakow, but I stayed there one day, enjoying the old town in 1990, and then we went to Zakopane and stayed in the Tatra Mountains for a few days. Okay, this was my first Poland experience. I survived it, as you can see, and many more followed. But let me, for now, just mention Würzburg. I was not born there, so I'm not Franconian. The people there speak Franconian, not Bavarian, by the way. But Würzburg is known for a few things. Among them is an artist who lived at the same time as Stwosz, as you pronounce him in Polish, and similar genius in his art. But other than Stwosz, he was not a big businessman, so he died rather poor financially. But he left many wonderful sculptures in and around Würzburg. Another thing that Würzburg is, or the surrounding of Würzburg is known for, is this company that's apparently also active in Poland. It's in a small place, just a few kilometers out of Würzburg, Iphofen, which has like 5,000 inhabitants. And the company is really huge. They have an IT department of, I don't know, 150 people just for the logistics. And the third thing I want to mention about Würzburg is the wine. If you hear Bavaria, you think of beer, but Würzburg is part of wine. The wine region of Bavaria. So this is the northeast of, so Bavaria is all this here, and only this small part produces wine along the river Main that goes through Würzburg. And here you can see one of the wine companies, Julius Spital. It's actually a hospital, but back then people were so happy when they survived the treatment, they gave whole vineyards to the Spital. And so they accumulated quite a bit over the centuries. And so now they are one of the biggest wine producers in Franconia. And Silvaner is the maybe best known Franconian white wine, as you can see. And this is from a specific vineyard, Würzburger Stein, which is in Würzburg, and it's like the best location. So Goethe said that he really liked the wine from this specific vineyard. Okay, now let's slowly move into the topic of today's talk. We have a lot of time, so I will not go fast, and I invite you to stop me if I am too sloppy in introducing problems or definitions. So what is graph drawing all about? Well, you all know graphs, and our job is to somehow squeeze them into the plane usually. Sometimes we also draw them in 3D, but that's a different cup of tea. So the main problem when you draw graphs is that most graphs are actually not planar. You can quantify this statement, and it's still true. But then you have to fight with crossings. And typically, the crossings are a pain for the people who watch your graph drawings. So you have to find ways how to deal with these crossings. And the obvious optimization problem that comes out of this is to reduce the number of crossings in drawings of graphs. Another option would be to take away elements of your graph that are disturbing. Yeah, so maybe there are some vertices that are incident to edges with a lot of crossings, and then you may want to not show this vertex or show it more in the background in gray or so. So this is also something that we will look at today. So can we remove a small subset of, in our case, edges, such that the remaining graph looks better? Okay. And the setting in which we will draw our graphs is a well-known one for people who look into book embeddings, where you insist that the vertices should be aligned on a, say, horizontal line, and the edges are drawn in half planes that meet in this horizontal line, which is called the spine of your drawing. And each edge must be drawn completely in one of these half planes. So you're not allowed to draw an edge that first is in the orange half plane and then maybe goes down like this and connects to this vertex. This is against the rules of our game. Okay, so this of course makes the whole problem of drawing graphs a bit more combinatorial. Yeah, you just map edges to pages, and then when do two edges intersect? Well, if they form such a pattern where the endpoints of the two edges that are involved in a crossing, where they alternate between the two edges. So it's really a combinatorial question now, not a geometric one anymore. Okay, and due to the seminar we were participating in, we were interested in fast, exact algorithms, maybe parameterized algorithms for problems that have to do with book embeddings for graphs. Okay, another option that will not play a role in today's talk is that you don't throw away edges completely, but you just show parts of edges. These are called partial edge drawing, and these have also been studied, but we will not look into this today. Okay, so this is the rough area where the talk will take place. Let me properly define the problem now. We are given an ordered graph, and by ordered, I mean that the vertices come in a given order that is encoded by this function sigma that just gives me the number for each vertex, yeah, from 1 to n. And additionally, we are given some positive integers, k, p, d, some subset of which can be parameters of our problem. And the question that we want to answer is, can we find the subset S of at most k edges of our graph, such that if I remove this subset of edges from my graph and keeping the same ordering of the vertices, can I then find a mapping of the remaining edges to the given number p of pages, such that every edge has no crossings or has at most a fixed number p or d of crossings.
So D-planar means what?
D-planar means that a drawing of the graph is D-planar if every edge has at most d crossings on it, is crossed by at most d other edges.
And the sigma is what you enforce to be on the spine.
Exactly, it's the vertex ordering on this.
Okay.
So that's part of the input. Okay, so one has to be careful how to phrase this, because usually if you see a problem name like this, then you assume that these are fixed constants somehow. But for us, this is not the case. We still see them as parameters. We have to put them somewhere, so that it's clear what we are talking about. So just to make sure that we are on the same page, let's check. What's the page number of K5? 2. Who needs more? 4. Sure. Who is asking for too much? 3. Why not 2?
Why not 2?
Because 2 half planes give you 1 plane, and then you would have drawn K5 without crossings. It's not completely true because you cannot go from 1 half plane to the other,
Yes.
but essentially it is true. Yeah, but I mean, if you had a 2-plane drawing, then a 2-page drawing, then it would actually be a planar drawing. Okay, so to continue in this direction, so how many edges do we have to remove to get what you assumed? Okay, 1 edge. Of course, 1 edge is enough. We can do it. So, but now we change the game again. So now we allow 1 crossing per edge. So how many edges do we have to remove in order to get the drawing on 2 pages? Well, none, of course, because the drawing that Piotrek was thinking about, it has only 1 crossing, and then this is a 1 planar drawing. Okay.
Oh, simple.
Or maybe to argue a bit, this was a bit hand-wavy. So what I should argue is take a drawing of K5 that has only 1 crossing, and now you move the vertices so that they lie on the spine, and you make sure that the edges don't intersect the spine. And you can do this.
Yeah, the router thing is not doing me.
Let's try. Oh. Can do it like this, right? It's a drawing of K5 with just 1 crossing. And now we want to go through the vertices such that all the edges are on one side or the other side. And what we can do is we just take a Hamiltonian cycle, and then every edge is either inside the cycle or outside the cycle, if we manage to draw the cycle without crossings. Yes. And if we are able to do that, so there are 1, 2, 3 edges inside, 2 of them cross, and there are 1, 2 edges outside. They don't cross, so this will be our 1 planar drawing of K5 on 2 pages. Okay, and just the last one. So if we allow 2 crossings per edge, can we do it on 1 page? Or do we need to remove some edges? So let's have a look. Put my 5 vertices on this, and this, I mean, if I just have 1 page to draw the graph, then everything is determined. And some, oh, all the edges have at most 2 crossings. So then we don't have to remove any edges. Okay. Good. Now I think the problem is clear. We have a couple of variants. I have not specified exactly which variant we are going to study, but that's what I'll do in a few moments. Let me first give you another tool how to view some aspects of this problem, namely the conflict graph. And the conflict graph is simply the intersection graph of the edges for the given ordering. So here's again a drawing of K5. Actually, it's the one I drew last, and you can see that every edge, I have every edge except for the outer ones. Every edge intersects two other edges. So the conflict graph of this drawing of this ordered graph actually is the C5. Okay, and if you want, you could add to this drawing also the missing edges. So here, every vertex corresponds to an edge, and an edge corresponds to a crossing. But these gray edges, they don't have any crossings, so they would be independent vertices. Okay, and such a thing is called a circle graph, namely the intersection graph of chords of a circle. In a way, you can see the circle here, but I drew it for you once more. So here now, the vertices of the graph correspond to chords, and the edges here correspond to intersections. So this is, in a way, this is just another view of this. Okay. So what does this have to do with our edge deletion problem? Well, suppose you want to delete edges to get a one-page drawing where you allow d crossings per edge. Then this is the same as deleting vertices from this graph, such that the remaining graph has at most degree d. So yeah, if this vertex has degree 2, so it means it is crossed twice. Which one is it? It's a bit hard to see. Let's take the green one. The green is clear. It's crossed by orange and red, and so it has degree 2. And if we want to remove edges to get to such a drawing, then it's the same as removing vertices from this graph, and such that every remaining vertex has degree at most d. And it's the special case where the graphs are restricted to such circle graphs that come from such a geometric background. And this can be solved in FPT. Okay. A little more related work. What's known about this area so far? So using this conflict graph, how can we express testing whether a given ordered graph has fixed vertex order page number p? How would we express it? So now, if I say page number, I mean no crossings. So yes, exactly. It's coloring the graph, the conflict graph, with p colors. Good. And in the special case that you have only 2 pages, then this is checking whether the graph is bipartite. For 4 pages, it's already known that the problem is NP-hard. And the same author claimed a solution, an efficient solution for the case p equals 3, so 3 pages. And just testing whether you can map all your edges to 3 pages such that no page has any crossings. But recently, some people have gone through this old article and have found several gaps in the proofs. Okay, so this is open still. Okay. Now another way to restrict the problem is that we actually the same. Now here we were just testing. Now we allow edges to be deleted. But again, we look at the planar case for each page. So what does this mean? So this is now it's not directly p colorability, but now we are allowed to delete edges from the graph. So it means we are allowed to delete vertices from the conflict graph. So it's vertex deletion to p colorability. Okay, good. And again, special case, one page. This is maximum independent set in circle graphs, which can be solved in, I think, quadratic time. And for p equals 2, this you basically want I mean two colorabilities bipartiteness, so you want to destroy all odd cycles, and you have to remove enough vertices in order to destroy all odd cycles. So this odd cycle transversal and FPT algorithms for this are known. Okay. Now, we've already mentioned fixed order page number. So that's the number of pages you need for a planar drawing on, well, the smallest number of pages that you need in order to draw, to map all the edges in the given vertex order to pages. And this has been studied, and it was it's a relatively new result still, where graph drawing problem and such a parameterized approach come together. And here the parameter is the vertex cover number. We've seen on the previous slide that the number of pages, the natural parameter, does not work because the problem gets NP hard already for 4 pages. So people looked for some other parameters. Okay, and another parameter is the path width of the ordered graph, which is not comparable to the vertex cover number. So this is a different approach with a different parameter.
True, doesn't work.
Not known yet.
Well, this is generalized both, right? Yes.
Yes.
Path width for sure, and that is the right answer.
Yes. Now here's another variant of the problem, fixed order book drawing, which means testing if there is a p-page d-planar drawing. So we are not removing edges here, but we are allowing more crossings per edge than in the problem up there. And for this, there have also been similar, algorithms with similar running times as up there, where you replace the 2 by a d plus 2 in the base of the expression. And the last previous work I want to mention, and the only one I quickly found that looks at the flexible vertex order case is the same paper, I think, as the one up here. And they look at the now not fixed order, but the normal page number, and they have an FPT algorithm for that, but it's double exponential. Okay. Yes. So the input size is additive here. Okay, now what have we looked at?
You just pre-compute something independent of the. That's interesting. Are these proofs hard, or
I looked into these. I don't remember actually. I think this is maybe not so bad, but this one, or it was the other way around. I forgot. One was quite technical. Okay. So what I would like to show to you today is how we can compute the fixed order page number in time that is single exponential in the number of vertices, or if you give me a number of pages that you want for your drawing, then I can give you a book embedding that uses exactly this number of pages and minimizes the number of crossings. So for the first result, all the pages are without crossings, and for the second result, you restrict my resource, the number of pages, and then I try to make it as nicely readable as possible. Okay. And these are very much related, these two things. The next one, if you don't want to wait that long, we can give you a fast approximation of the fixed order page number, even for general P. Then a result that I will not show to you today is how to decide in, sub-exponential time in K, where K is the number of edges that you are allowed to delete. To decide whether it's enough to delete K edges in order to get a D-planar layout on a single page. And this result is achieved by separators and recursively subdividing the graph. Yes. All our results are just for the fixed vertex order.
Oh, this one as well.
Yes, ordered graph.
Ordered graph, yes.
And finally, the last one that will take most of the time is has a new parameter in it, namely the size of a hitting set, where here's a simple example. This set of edges has a hitting set of size 1, so it's a point on the spine that is contained in all the edges. Yeah. And if for such instances, basically where your graph is bipartite, then we can solve the problem efficiently. But if the hitting set is larger, then we have an XP algorithm with respect to the parameter h plus p. So the number of points in your hitting set plus the number of pages. Okay, so let's start with this part, which is to warm up a little bit. It's not cold in this room when you stand here. It's only cold when you sit there and suffer. Okay. So we want to compute the fixed order page number in basically 2 to the n time. And one related result that I probably have not mentioned yet is an algorithm that solves the problem of deciding whether you can actually distribute the edges to a given number of pages with at most a given number of a budget of crossings.
CR is just
the number of crossings.
What number is not C times R?
No. Sorry.
Yeah, sure.
Like the path with this is computer science notation. Okay. It's incomparable to our result because our result has the input size in it with 2 to the n. And here this is the graph parameter, but the base is really, really large because, or can be very large. Okay, to state my result, let me define CR of P of G comma sigma of an ordered graph to be the minimum number of crossings over all possibilities to assign the edges of G to the P given pages. And with that, I can state my result. So given some number of pages, an ordered graph, and vertices and edges, we can compute the values CR1 to CRP of our ordered graph in 2 to the m times some polynomial in n time. Okay, what does this mean, first of all? Well, if we give ourselves a budget of p pages, then we can compute such a p-page book embedding using the minimum number of crossings, maybe this number of crossings in the given time.
So, Sasha, just to get the comparison right, so in your results, what you say is what is this? What is like the strength of it? Is that the exponent that with n is constant, absolutely constant. Where with the other results,
the part of the running time that depends on the size of the input is just linear in their case. But I mean, they have this potentially very big base of the
this how does it relate to n? It's most like.
I mean, if you have a graph that can be drawn on p pages such that it has only a single crossing, then this is not so bad.
Yeah? But then like the upper bound would be
upper bound. I mean, in the worst case, every edge crosses basically all the other edges, so it's n squared. So n squared in the base.
I see. So that's why it's incomparable. And with the other results, the results before that were kind of computing this with some other parameters being fixed.
Yes. So
always also like you have number of edges, and over there you had what did you have? Like 2 to the path width.
Yes, here they did not minimize the number of crossings, but they asked for the minimum number of pages such
so
that you can.
Okay, slightly different.
Yeah.
So there's no okay.
There's no direct. I mean, this is the only direct competitor, so to speak, to our result.
Thank you.
Okay. Yeah, it's there are really several dimensions, and it was for us also a bit overwhelming at the beginning to see what exists and how do we compare to these existing works. Okay, what else can we get? Namely, we can compute, if we have these values, we can compute the fixed order page number in the same amount of time. How do we do it? Given these values, quick check whether you are already asleep or not yet.
Which is
yes, you go through these numbers and you stop when you have the first number that is a 0, because that's the number of pages that you need. Good. Okay. Now let me try to prove this theorem. Little side remark. This Q, it's I mean, you only have to use as many pages as you have edges, obviously. Yeah, you don't have to go forever searching for the 0. It will appear sooner than later. Okay. Now, that's maybe one of the takeaway things of this talk. If you have not seen subset convolution, here you will see it in action as a black box. I will not talk about the algorithms behind it, but we will simply apply it to solve our problem. Okay, but first, let's go slowly. First, given a subset of our edges, let me introduce this notation. I'm not sure how legal it is, but what I mean by G induced by the set of edges, it's G induced by the endpoints of these edges. Yeah.
So there might be some other edges, yeah?
No. Oh, sorry. No. I really mean, maybe I should have written it differently. I thought, it's a nice compact way to do it, but probably the better way would be B of G with these edges.
Also, you have these. So you have these vertices that are not an endpoint, as an isolated vertices.
Yeah, but they don't
contribute.
So for this talk, allow me to write this as short form for that. Okay.
You define it. You allow yourself.
Good. Legal enough. All right. So what is this? This asks basically for the number of crossings I have in my set. Yeah, because everything is fixed. So the ordering of the endpoints of the edges is fixed. So I know exactly which edges, which pairs of edges intersect and which don't. So it's really just the number of edges in F that cross each other. Okay, and how can I compute this quickly? Actually, I can do it in linear time. Now I have drawn my edges just as intervals, but I think it's clear. I will give you a super simple algorithm that assumes the edges are all directed to the right. And we start with, we keep track of two numbers. The first one number is the number of active intervals or edges, namely those that intersect my blue vertical sweep line that goes from left to right through my set of edges. And the other one is the number of crossings that I have so far. Yeah? And now I count, okay, here I have three edges that leave V1, so that's the number of active edges in the beginning, and I haven't had any crossings so far, so nothing has contributed to this number. And now suppose I'm at some intermediate vertex Vi. Just before arriving at Vi, what do I have to do? Okay, some edges end in Vi. So this is the in degree of Vi that tells me how many edges end, and these edges stop being active. So I update A by subtracting the in degree of Vi. Okay, what else do I have to do? Now I'm in Vi. Now I can count crossings. How many crossings do I get? Well, the number of active edges, the number of new crossings that I get is the number of active edges times the number of new edges that start, which is the out degree. Yeah? So to my current count of crossings, I add A times the out degree. Because all these edges now kind of overlap and cross each other. Yeah?
Wait, so the graph, the G graph, is it this circle graph or overlap graph, or
it's
which graph is it, or is
this graph?
It's this graph. It's simply this graph. Okay, but then why do you have these crossings? I don't believe you.
Yes. I see a little error. You're right. Not all the edges that leave Vi. Yeah, they could end before the active. For example, here this active edge runs further. Okay, so forget my too fast algorithm, but I think it's obvious that you can do it in quadratic time. So you just go through all pairs of edges, check whether they intersect, and then you get something. Okay, good. So that means we can compute this number for all subsets of the H set in, well, there are 2 to the m subsets. For each of these subsets, we now need m squared time. So it's m squared times 2 to the m.
Okay.
Okay?
There you have m.
Yes, because I was assuming linear time.
Ah, m squared, of course. Yeah, sure.
In the paper, we only state n to the order of 1, which is 2. Okay. And now, okay, so we have all this knowledge about doing things in one page, but now we want more pages. Okay, so now how would we compute the crossing number on Q pages for a subset F of the H set? So this is dynamic programming, right? So the crossing number for Q pages for this graph that I've defined over here is the minimum over, now I take all the possible subsets of my set F. And what do I have to do in order to get the right number? Ninja?
Present the Q minus 1, here prime, and present 1, 2, and 1.
I have barely heard it, but I'm pretty sure that you said exactly this. So we put this subset F prime on one page and find out how many crossings it induces on this one page. And the remaining edges we put on the remaining Q minus 1 pages. And if we have this table and that table, then we can compute this table. Okay? So if we do this in brute force manner, then we need how much time? Well, each minimum computation goes over all subsets. So we have n choose I possibilities to choose F. And for each, we go through all the 2 to the I subsets, F prime. So what do we get for this? You guys know this. I had to think for a moment. 3 to the 3 to the exact 3 to the m. Yes. Okay. And probably we need m squared here because of the squared here. Okay. So now we would like to improve, and that's where subset convolution comes in handy.
You also improve from 3 to the m to 3m?
Yes.
Okay.
So we define 2 functions that map subsets of our H set into some ring that has the right operations that we need, the minimum and the plus. And then subset convolution tells you, okay, which 2 functions? Good question. We take as the first function f, we take this thing for some subset f, and the second function g gives us this thing for some subset f. Okay. So one has the crossings on one page and the other one has the crossings on q minus 1 pages. And if these functions can be bounded by m squared, and then this convolution of these 2 functions, which the standard way of writing is using the sum and the multiplication here, but actually in our ring, the sum corresponds to the minimum and the multiplication here is the plus. So this thing can then be computed in 2 to the m time. Via some miracle. Okay? And for us, this means that we pay this setup for kind of the first column of our table that refers to one page. And then using this trick, we can, in this time, we can compute the next column of our table for all the subsets and so on. So for each page, we pay this effort. So in total, we get P times this effort.
So is it this result subset convolution, is it also dynamic programming? Or in some
Möbius transforms and
I see.
tough stuff.
Nice.
I have not looked into it. Okay. Good. Now, in case you are unhappy about exponential time algorithms, here I can help you. But of course, we have to give up exactness. So I will give you a fast approximation algorithm instead. Just to remind you of something that was probably lost in the first few slides. We can efficiently, namely in quadratic time, compute a smallest set of edges whose removal removes all the crossings on one page. Remember the tool? Maximum independent set in circle graphs. Valiente. Okay? Good. And this we will now use as a subroutine for this result. Okay? It's not a great approximation, it's just log n, but it will give you, I have not stated the running time, but if I talk about approximation, I mean, of course, efficiently. Okay? What do you think when you see an approximation factor that is logarithmic? Set cover, yeah? And set cover shows up here, but let's go slowly. So here's a set of a family of sets, namely of all those edge sets that can be drawn on one page without crossings. There's many possibilities, many subsets of our edges will have this property. Potentially, of course, it's of exponential size. So I don't really want to write down this whole set family, but I can define. Okay, and if I take any subfamily of this family F, then it's a good solution if all edges are covered by F prime. And by good solution, I mean it's a feasible solution of this set cover instance where I want to cover all the edges. Yeah? I want to put the edges into crossing free subsets, and I want to use up all my edges. Okay. Now, if I have such a family, then I have a drawing, because each set in my set family will go to one page, and we are done. But that means that any optimal solution of this set cover instance, where we have to cover all the edges by subsets from F, yields also an optimal drawing in terms of the page number, and also in terms of any approximate set cover solution yields an approximate approximation of the page number. And now, okay, of course, for set cover, we know a log-n approximation, namely the greedy algorithm. So we want to compute the solution to the set cover instance, this one, by greedily adding sets F of this type. And which one do we choose first? Well, first of all, we take the biggest one that we can find that doesn't have any crossings, and we can find it using this lemma. And then in the next step, the second set that we want to find is the one that covers as many uncovered edges as possible. That's how the greedy algorithm works. Now, how can we avoid writing down this set cover instance, which is too big? Well, we use the lemma, of course. The first step is clear. And then for the second step, we just throw out from the instance everything that we have covered already. And then we have a smaller instance, and we can run the lemma again. So we keep applying the lemma to the graph minus what we have covered already. So we remove from the graph all the edges that we put on the first page, then we find a solution for the second page, remove all these edges from the graph, and keep going. So each step of the greedy algorithm then can be implemented in quadratic time. And the whole algorithm then takes p times n squared time. So that's an approximation algorithm for the case of planar pages. I claimed in my overview, we can extend this to d-planar, and actually the solution is the same. We compute the same solution, but since if you admit a certain number of crossings per edge, you cannot save so many pages. So the d-planar page number is not much smaller than the planar page number. And so the same solution gives you also an approximation for the non-planar case. Okay, so finally, good in time. Let's move to the new parameter, hitting set, size of the hitting set. So let's first check how much time would we need for a brute force solution. So what would you do? You want to map. You want to map your m edges to p pages, but you allow to delete edges. So for each edge, you have p+1 possibilities, pages 1 to p, plus the possibility of deleting the edge. And so this gives you, how much this will give you, check for each edge. Okay, and then you have to run a check whether the solution that you get by your mapping is actually feasible. So whether every page is crossing free. And another way to say this is whether the edge set forms an outer planar.
Well, this outer planar graph must have the same walk.
Yeah, but it really is. I mean, you can test the autoplanarity by adding the spine edges and then testing for planarity.
Yes. And
so you can do it in time linear in the number of vertices, and this is the number of mappings that you have to check. Okay, so this is the baseline comparison. Now, our new parameter is, as I already said, the size of a hitting set. And the good thing about it is, first of all, can be much smaller than a vertex cover. Think of a complete bipartite graph. Oops. So I have some vertices here, some vertices here, And here's my hitting set, and you have all the edges between here and here. Then for this complete bipartite graph, you have to take one set of your bipartition in order to cover all the edges. But here you need just one vertex to hit everybody. So it's a good parameter. It's a small parameter. And the other good thing about it is that you can compute it very easily, other than the vertex cover number. Yeah? So I again have a simple algorithm. This time it should work.
Let's see.
So let's see. We again go from left to right, and it's a kind of a lazy algorithm. So it only does something whenever it must really do something. So before you leave the first interval, you place a hitting point. So this kills a number of intervals, and then you repeat. You go as long as possible, and if you cannot continue because you would leave one interval unhit, you put a hitting point. And this should solve the problem in M-log n time.
Yeah, you need at least 3 crossings in this graph because there are 3 different intervals, and each of them needs a cross. So that's a proof.
Yes, I agree. Good. Okay, so here's the exact statement for the special case of hitting set of size 1. So roughly cubic time. Okay, and maybe this is also some nice thing to take home. How we use some well-known tools to solve this problem that nobody really had thought about before. Okay, so here's my intervals. Here's my hitting point. It hits all the intervals. And now, what is the kind of structure that helps us? So if 2 intervals are contained in each other, this is good. We can put them on the same plane, on the same page. Sorry? If they are not contained in each other, our hitting point is here, it means they cross. So we are really looking for families of contained intervals, because this is the only thing that we can put on one page. Yes. So let's make a graph. More graph. I'm not a poset person. I need graphs. So here's a directed graph, namely the containment graph.
It's perfect, yeah.
Maybe
We want to color it.
we want to. What do we want? What do we want actually in this graph? A good question.
So, but you draw an edge when there is a containment, yeah?
Yes.
But then you want to split it into clicks, yeah?
No. Oh yeah. Okay.
So if you draw
Okay.
it this way, yeah?
Yes. 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 Okay.
But
Yeah, you're right. It clicks, but I saw it more of like a path problem. So I want chains.
So you are a poset person. You just don't want to.
Okay. And here you can I mean, and the number of chains that I want is given to me, right?
Yes.
I want to cover as many of these guys by p paths, and in this case, I managed to cover everybody except for one guy. I mean, you could move this. What could you change?
Okay.
You could maybe, instead of these 2, you could maybe cover these 2, but then, or you could go from here to here, from here to here instead of to here.
So you have a cyclic directed graph, and you try to say how many elements can you cover with p paths.
Mm-hmm. How would you do it? Ah, any ideas? What's the hammer?
I wouldn't do it. Like, if it's doable, then probably greedy or do it.
Yeah,
Yeah.
you need some more global thing, I think. Really would be tough.
Okay.
Smart recursion.
Sorry?
Smart recursion.
Smart recursion? I've never done smart recursion. It was stupid recursion.
Some kind of bipartite matching.
So how do you solve bipartite matching? What would be a hammer that solves bipartite matching?
For position of one big pass, I don't know what you like.
Yeah. Okay, basically it's a flow problem.
It's a flow.
You see the flow network? Okay, we start with a source S. Then we have an edge of capacity P, because we want P paths to a second source S prime. And now we connect S prime to all the vertices that you can see over there. And on the other side, we have a super sink T, and we connect everybody to T.
The known capacities are one now, right?
All the other capacities are one, and now we still need we need some rewards in order to cover as many vertices. So what do we do? How do we model a vertex? It has something going out to T for sure. There's something coming in from S prime. And so I split my vertex into two. And here I put a cost. And the cost must be negative, so that I will get a minimum cost, that a minimum cost flow will maximize the number of original vertices that I traverse. Yeah, and from all the incoming edges from other vertices, they come in here, and all the outgoings are attached here.
So the flow you will pay as many times as the number of paths you have.
No, as many as my paths cover vertices.
As your path, yes, true, actually true.
So the capacity thing. So I will ask for a maximum flow. So to make sure that I get P paths, but among all the maximum flows, I want one of minimum cost. And so this is the trick.
And then, but the other edges from this vertex to other vertices go from the vertex below, right?
You just split up. So the incoming edges arrive here, and the outgoing edges leave from here. So that if a path wants to go through this vertex, then it needs to arrive here. It gets its bonus, and then it goes on. That's it. Is it clear?
But then you pay every time you use a vertex, so you.
Yeah, but you pay -1.
Ah, -1, okay.
Yeah, that's good. So you want to cover, and the capacities make sure that only one path can go through.
Fair enough. Okay.
Yeah. So all these edges have capacity 1. Okay, very good. Yes. Because of this capacity constraint. We cannot have a higher value, and we can obviously push P paths through. So the maximum flow will always have value P. And among all those value P flows, we will take one of minimum cost. Okay. Good. Now we have 18 minutes to prepare for the big thing, the XP algorithm. XP sounds a bit boring, you know, everything is XP. No, it's not that easy, apparently, for this case, at least the way we did it. A small thing beforehand. So here are some edges that all go across the same hitting points. This pair of edges is on page 1, this pair of edges is on page 2. Maybe we have more pages, but then it's difficult to draw. So we say two such sets of edges are compatible if the E edges and the F edges have the same number. And we can enumerate them as I've done it here, such that the E edge is always contained in the corresponding F edge. Contained meaning as an interval. Yeah? The smaller interval is contained in the bigger interval. Okay. So I take for the remainder of the talk, allow me to use E for some arbitrary edge set, while E of G is all the edges of my graph. Then I don't need some tildes and bars and so on. Okay, now here's a lemma. We are still in the hitting set of size 1 case, but now we want to solve a variant of our problem. And the variant is that we are additionally given such a two subsets of edges, yeah, of size P, as many as we have pages. And now we can decide whether they are actually compatible. That's not so hard. And at the same time, if this is true, then we can solve a version of our problem such that on each page, we are only interested in edges that fit between E1 and F1 and E2 and F2. And we want to maximize the number of things that we can stuff into them together.
So, but when you set two sets that are compatible, do you fix the actual matching between them? Because you're free to choose.
Yes.
And you want to maximize over that as well.
And the algorithm does it for you. No, you don't maximize. You specify these sets of edges. But you get the matching together with a solution. You cannot prescribe the matching. That's okay. A problem that we initially oversaw, but it has to be solved. So what do we do? I mean, the only tool we have is this one. So we have to modify this tool such that it does this. How can we make sure that the edges that are in our solution, that are covered by our paths, are only between these two guys and between those two guys? How can we do it? Yes?
Well, we don't put a flow, like we put no capacity for going like maybe.
Well, we still want P paths, right?
Yeah.
For P pages.
Yeah, so we put the P.
Yes.
But like for a given vertex, we just don't put. Oh, just like for the S primary, we just don't go like to every vertex but only to.
Only
E.
to E edges, right? So this is to E1, E2, all the way to EP. And similarly, we only have outgoing edges from the F edges. from F1 to Fp. And this is all. And when are the two subsets compatible? I mean, using the flow, what does the flow tell us about the compatibility of E and F? If the flow value is P.
Yeah.
Exactly. Okay. This is it says here a hitting set of size 1, but it will be the main ingredient for the general case. Okay, so here's the general case. General means I have 3 hitting points and 2 pages for now. I need a little bit of notation. So you remember these E and F edges that kind of delimit the choice, and I have a new index that tells me which edges, which points in my hitting set are bridged by these edges. So, for example, the edges over here, they only bridge C. The edges here in this thin purple strip, they bridge B and C, and so on. Okay, so we say an edge bridges a certain subset of the hitting set. If it goes across these, and I mean, this one would not bridge C, because I can extend the hitting set to B and C. So it bridges only B and C, not B and not C by itself. Okay, and this subdivides my edge set into subsets that according to which part of the hitting set is bridged. So, for example, here I have maybe some edges, maybe not only this one that I've drawn in this wonderful solution that is planar and everything, but in my graph I may have more edges, and this red edge now is another example of an edge that bridges B and C. So it's part of this subset EBC of my edge set. Okay, the gray edges are in A, ABC, and so on. And now the main insight to get a solution for the general case is that actually, although this gray stuff has bridges 3 points of my hitting set, it has the same structure as a set of edges that bridges only 1 point. So we already have the tool to deal with it, but we have to stitch things together. And that's the difficult part. So we split into instances of the same type that you have seen before. And we work with this adjustment to the flow network that we have already seen. And a minute. Okay. So let's at least understand what the difficulty is. Suppose I have a solution, a subset of edges that I can map to my P pages, and then I want to use EQ to talk about the edges on page Q. And now the edges that get mapped to this one page Q, they bridge various subsets of my hitting set H. So let me use XQ to talk about these subsets. Let me go back once more to give you an example. So on this page 1, which is the upper page, what would be the family X1? It's A by itself, B by itself, C by itself, BC, because of the purple ones, not AB, and of course not AC, that doesn't make sense, but then additionally ABC. So the only subset that is missing is AB, yeah, in the family X1. Okay, a side note, these set families are all laminar. So you cannot have two sets inside that overlap. They are either contained in each other or disjoint, but no overlap. Okay. Now we are moving towards XP algorithm, so we need to somehow encode our solutions. So what's encoding for the solution on a specific page Q? Well, it's the sets of the subsets of my hitting set that we bridge, and for each such subset, we look at a pair of edges, the outer and the inner one, and everything on that page needs to fit between EQX and FQX. Okay, and if we use this to encode the solution on page Q, then E1 to EP is an encoding of everything, of some solution E. Okay. Now, what is the difficulty? Back to the question. If some subset X of my hitting set is bridged only on one page, maybe an optimal drawing, then our task is easy. We just must apply the previous lemma that tells us how to squeeze as many edges between E1 and F1. But if this subset of the hitting edge is kind of active on other pages as well, yeah? So if this set QX, which is a set of pages that all have edges mapped to them that bridge the same subset of the hitting set, then it's not clear which edges should go where. So if this set is greater than 1, it has cardinality greater than 1, then the choices of which edges are drawn on which of these pages among the ones that bridge X, they are suddenly not independent anymore. And that's where we got stuck at some point. But luckily, we found a solution, which is written down in this main lemma. Let's try to understand what it says. Okay, again, let's use E for some solution with a given encoding. The encoding is what we will guess. So, okay. So for every subset of the hitting set, this says, well, some edges actually bridge this set of hitting points. Let EX and FX, the sets of edges that that are part of my encoding for some page. Yeah? So I put all the E edges that bridge the same subset X into the subset, and all the F edges into the other subset. And now I can apply lemma 1 with respect to this subset of E edges and subset of edges and check whether they are compatible. And if yes, I can get a solution. And this solution I call SX. It's a solution of all edges that all bridge the same subset X of my hitting set. And now my claim is then, if I do this, then I simply can take all the subsets as X and put them into a box. And this is a solution that is at least as good as the solution I started with. So it's a kind of an exchange argument that you can see happening here. And that's exactly the proof. So let's take some subset of our hitting set, and now we will exchange the part of our solution E that has edges that bridge this subset X by SX. We will exchange it. and then we can only make it better. Okay, so that's the main insight. So let's take a page that has edges that bridge X. Okay, then we look at the edges in the solution on that page Q. Okay, on the page Q, where this edge from our set EX ends up. Okay, and now we're not sure whether the pairing is the one that we kind of had in mind. So we don't have any connection now. We lost the connection between the E edges and the F edges. So we just look for the corresponding F edge. The unique element of the set that corresponds to this E edge, but it has a different number. Okay. And now we make a drawing of the edge set where we throw away all the edges in our solution E that we start with that bridge the set X and replace this EX by our solution. And we claim that this makes things only better. Okay, so here you see a drawing. So we have some edges that we are worried about, the ones in here, the ones in there. There's something inside we don't care about, and there's something outside we don't really care about. Everything now happens between these pair of things. But we may start with something like this and end up with something like this, where this edge E1 is paired actually with that edge F2. And this is paired with that one. So things flip, can happen, but our argument is that even if it flips, we can still squeeze the maximum number of edges into that region. So the idea is the following: take an edge Q that does not have edges that are bridged by X. In this case, we just take the part of the given solution and we don't change it. Now, if we have a page where there are actually edges that bridge X, then we construct a new part. Yeah? We modify what we have. How do we do it? We remove those edges that are contained in the outer edge. We add the edges of our solution, SXQ, and we add the edges that are contained in the inner edge. So once more, we have an outer edge, F something. We throw away everything, and we replace it by our solution. That's the SX part between FX and EX on this page Q. Everything happens on page Q. So we take the old part that we have not touched. We put that back into the solution, but the main thing is we changed everything that was below Fx by our solution and the old stuff. And we do this for all the pages that have edges that bridge X. So yeah, we replace up here, we replace it by our solution plus the old inside, the inside in E1X, And down here, we do the same thing. We throw everything away, and then we replace it by our solution and what used to be inside a E2X. And now the only argument is it fits into this little box. This modified thing is now also a feasible solution of the flow network. But our flow network gives us the optimal solution. So that means that the solution that we have obtained by this exchange is at most this good. Sorry, this is the old solution. So the old solution is a feasible solution of the flow network, although we did not create it using the flow. And so the flow gives us the best possible solution. And that means that the edge that I started with is at most as good as the edge that I get by this exchange. And if I repeat this exchange, in the end, I will get the solution should be curly as that I get by doing this for all subsets of my heating set. So this is not an algorithm, this is an exchange argument that tells me no matter how I start with any feasible solution, I can get to an optimal solution by replacing things using my flow network. And the algorithm itself then does the following. So again, XQ was the family of subsets of my hitting set that are bridged on a certain page Q. This subset, because it's a laminar family of sets, cannot be so big. Here's the argument. Start with all the points in the hitting set, then look at all the sets in your family that are minimal, and then look at the next level and the next level and the next level, and you start with H points, and in each step you move together at least two previous sets, so in total you get at most 2H minus 1.
It's a tree.
Sorry?
It's a tree. So.
Yes, yes, exactly. It's a tree. Funnily drawn tree, containment tree. Mm-hmm. So that means that such a partial encoding on a specific page Q chooses, well, 2 times as many edges, the E edges and the F edges, the outer and the inner edges. So 4H minus 2 edges of type E or F. And that means the total number of encodings that we can get is we have to map edges to pages, and each page can get this many edges. So it's M for the number of edges times P for the number of pages times the number of edges that we get on a specific page. Okay, and now for each subset of our hitting set, we apply lemma 1 in cubic time, roughly. If 2 subsets of the heating sets are different, then it means also the edges that are bridged by them are disjoint. So actually, for each encoding, we only spend cubic time in total. Okay. Although we have to apply our lemma 1 several times. Okay, and now we just put it together, and we get total running time. That is XP in H times P or H plus P. It's the same. Good. Many of the problems. Sorry for overrunning. We'll start by thinking that 90 minutes can never be filled, but then here we go.
Thank you.